So our last video ended by just looking at what a few of these equations for lines can look like. What I want to suggest to you now is that these lines are actually more interesting than you ever thought they were when you were in high school and learned algebra for the first time. And that's because in the real world, if we have a regression line that's been derived from actual data, we can use it to predict things. So if we have a line like this, we can predict the value of y simply by knowing x. That may not sound very interesting, but it all depends on what you substitute for things like y and x. So for instance, at Point Loma, if we want to know what your college GPA will be, but you haven't gone to college yet, people can use things like your high school GPA. People can use things like your SAT score. People can use, if they've coded them right, things like letters of rec. And what people would do is to use, so for instance, our admissions department would use all of these criteria to try to predict your success at Point Loma. So for instance, if we had an equation like this, y equals 2x plus 1, and let's say, again, this won't apply exactly to your high school GPA, but we can imagine it. If we knew, let's say, well, let's imagine the GPA went on up through 7 or 8 or 9, and we knew that your high school GPA was 3.0, and this is our regression line, this is our regression equation. We just simply enter in that x equals 3, we put it right into the equation, and now we have y equals 2x, and our x is 3, plus 1, or 2 times 3 plus 1, which would give us 7. That is a nonsensical GPA figure. Although the way California curves their high school GPAs, you never know. Maybe someday we'll end up with a GPA of 7. But the idea is that you can make a prediction about something unknown based on something known. This becomes useful because oftentimes we want to predict behavior in the same way. So we know something, but not something else. We know x, but not y, and we'd like to be able to guess what y will be. We may know how tall a basketball player is, but not how many points she will average in a game. For instance, in a situation like this, regression could help us to estimate the value of a second variable based on a known variable. So if we had a collection of data about a series of, for instance, female basketball players, and we knew their height, and we knew their points per game, and we plotted all of those in space. So you can imagine height along the bottom right, or along the x-axis, and then number of points going up the y-axis. If we were to look at those in space, so let's take it and imagine it for a second, we have height, we have number of points, and there's very few basketball players that would start out being this short, so we're not going to have many data points over in the really short range. But what we may find is the taller our basketball players get, the more points on average they score per game. If we have a line of best fit that goes through those, this line or this regression line is going to help us use information about their height to then determine or predict how many points per game they would score. In other words, y equals ax plus b. Our regression equation looks similar to your linear equations, except now we're going to use slightly different figures. So in a regression equation, again, where we're trying to find this unknown variable, we have y. This is going to look the same. We also have x. This is going to look the same. So both our y's and our x's look the same. What's different is now, instead of our normal slope term of a, or some of you guys might have learned m, what we're going to call that now is beta 1. And instead of our y-intercept, we're going to call that beta 0. I'm going to take note of the fact that there's a u here, but from here on out, don't pay much attention to it. U is simply an error term that gets attached to this to indicate that this is imperfect. We will not be able to perfectly predict a person's score on y from x. There will always be some error associated with it. So in this case, for instance, in our basketball example, y is variable 1, or what's called our criterion variable. This is what we are concerned with. We want to predict, here in our example, how many points that person will score per game. X is our second variable. This is actually our known variable. This is what we call our predictor variable. And our predictor variable in this case was the basketball player's height. Like I said, U is an error term that essentially all you need to know is that these regression lines are always imperfect. They're always going to have error associated around them. We'll talk about those later. Those are called deviation scores. But for right now, just know that a typical regression line has this factor of U. And once we have this equation that we're going to learn how to calculate in just a little bit, once we have that equation, we can actually plug in a value for X, so plug in a height, and get an estimate for score, how many points that person will score in a given game. The key, and this is where all of calculating regression comes in, the key is to figure out what are these beta values, beta 1 and beta 0. In other words, what is the slope of the regression line, and where is that regression line going to intersect with the y